Hello everyone, I'm Lee Zhongri from Nanyang Technological University. Today I'm honored to introduce our work, Splitting Light for Natural Light Uncalibrated Photometric Stereo. In this paper, we aim to solve the problem of uncalibrated photometric stereo under natural light conditions. That is, given a set of images about an object captured under varying environment light, we reconstruct not only the 3D surface of the object but also the lightings and materials properties. This problem is extremely challenging as it involves many unknowns and ambiguities among light, material, and shapes. To mitigate the inoppositeness and ambiguities of this problem, we propose a new problem setup called the spin light setup. This spin light setup assumes each image's light source is derived from a uniform environment light, aligned with a 1 degree of freedom single-axis rotation. Compared to previous method considering isolated light for each image, our method doesn't require a unique light model for each image due to the correlation of light between different images. We significantly reduce the unknowns for the light model by only modeling a unified light model with some low degree of freedom rotation matrix. Other benefits of this setup is we can derive a novel environment light initialization method, which is crucial for the unsupervised method to mitigate the ambiguities. It can significantly reduce the ambiguities between pairs among the environment light, material, and shapes. To derive a good light initializations, under the spin light setup, we extract information from object's boundary pixels based on the insight that the pixel values at the object's occluding boundary reflect the information about environment light. Specifically, we align a batch of images with their corresponding rotation matrices. Those matrices are uniformly initialized and will be optimized later. We multiply object's boundary normal by the rotation matrix, which is identical to rotate the object's boundary. We further record their pixel values plus the rotating normal as a pair. After rotations, the normal vector will form a sphere, where we map the pixel values to obtain the initial light map. Here we show the whole pipeline of light initialization method. Note that to improve the accuracy of the initial light map, we implement several filters and pre-processing steps. Next, let's briefly introduce our framework. This framework is developed on our previous work, DALI-net. First, we obtain the pixel coordinates belong to the objects in the image. Using these coordinates as the input, we pass through two multilayer perceptrons to obtain the material and normal of objects, combined with the light and rotation angles. We then render the images using the severe Gaussian render. During optimization, we calculate the L1 loss between the rendered images and the ground truth image. This loss term, combined with other regularization terms, is used to update the nullable parameters in the entire rendering framework. In practice, we found that optimizing this framework is time-consuming. Therefore, we propose interval sampling to downsample high-resolution images into many low-resolution ones, which are used to train the entire network. This approach significantly improves the optimization efficiencies and reduces the computation cost. Compared to patch-based downsampling strategies, this method better preserves overall object information, enabling regularization terms to work better. However, it may introduce aliasing issues. Therefore, we propose shrinking range computing for anti-aliasing. It also avoids local minima at the early stage of training. In the experiment section, we validate our method on both synthetic and real-world dataset. We generate the synthetic dataset using Blender. When acquiring the real-world dataset, we utilize a custom device. The experiment results demonstrate that even compared to the latest supervised learning-based method, we achieve state-of-art results in estimating surface normals on synthetic datasets. At the same time, our estimated lighting is also reasonable, reflecting the actual positions of the light source. On real-world dataset, through cross-comparison of reconstruction results from indoor and outdoor captured images, our method shows more robustness compared to supervised learning method. Here, we also show some relighting results. That's all about our work. Thank you.